Hello friends, welcome back to my channel Engineering Mathematics DJ Ganit. In this lecture we will discuss this question on finding inverse Laplace transform of this function. This question was asked in GTU Summer 2020 exam. Here given function is a rational function and the degree of numerator is 1 and degree of denominator is 1 plus 2, that is 3. So because degree of numerator is less than degree of denominator, this is a proper rational function, and as we know, proper rational function can always be written as a sum of partial fractions. Here one factor is s minus 1, another factor is s square plus 2s plus 5, and we know that we cannot write s square plus 2s plus 5 as a product of real linear factors. This is not possible, and this you can check by calculating the value of delta, which is b square minus 4ac. You can compare your factor with as square plus bs plus c, and you can decide abc and find out this b square minus 4ac. If we compare with this standard form, if we compare this factor with this standard form, then a equal to 1, b equal to 2 and c equal to 5. Therefore b square is 4 minus 4, a equal to 1, c equal to 5. This is 4 minus 25 and it is going to be negative 4 minus 20, not 25. So because b square minus 4ac is negative, we cannot factorize this into linear factors which are real or in real variable s. We cannot write this quadratic factor as a product of two linear real polynomials. Therefore this is irreducible factor. So every time whenever we have quadratic factor, we have to check whether it is irreducible or reducible, and that you can check by finding value of this delta equal to b square minus 4ac. If b square minus 4ac is positive, then we can factorize our quadratic factor into linear factors. If b square minus 4ac in this type of quadratic factor is greater than or equal to 0, then this we can write as product of two linear factors, say s minus p into s minus q. And if b square minus 4ac is negative, this cannot be factorized as a product of two real linear polynomials in s. So here s square plus 2s plus 5 is irreducible polynomial. So once we decide this, now we can write this as a sum of two partial fractions. One partial fraction corresponding to linear factor s minus 1 and another factor corresponding to s square plus 2s plus 5. So here I write one fraction corresponding to s minus 1, another factor corresponding to s square plus 2s plus 5. Here degree of s minus 1 is 1, therefore here we write constant a, that is polynomial of degree 0. Here degree of s square plus 2s plus 5 is 2, therefore in the numerator we will write polynomial of degree 1, suppose b into s plus capital C, where a, b and c are constants to be determined. Now we know the routine method. First we multiply whole equation by this product, therefore 5s plus 3 equals s minus 1 will cancel out here, and we have a square times s square plus 2s plus 5, and with bs plus c this will cancel out and we have s minus 1, and we give this number 1. Now we have one linear factor s minus 1 and this becomes 0 for s equal to 1. So we put s equal to 1 in equation 1 and we see what we can find out. Put s equal to 1 in equation 1, So left hand side will be 5 into 1, that is 5 plus 3, and here a times, here also we put s equal to 1. 1 square is 1 plus 2 into 1, that is 2 plus 5. This term will be 0 when we put s equal to 1. Therefore this is 8, and here also we can see this is 5 plus 2, 7 plus 1, 8. Therefore a equal to 1. We have obtained one constant using linear factor. Now to obtain the remaining two constants b and c, now we are not having any other linear factor, so we will compare the coefficients of equal powers of s on both sides, and we will see first we want to decide b and c. So we can see, if I consider this b into s, if I multiply this with s minus 1, I will have b into s square minus bs. So to obtain this constant b, I can compare coefficients of s square or coefficients of s on both sides. So suppose I compare coefficients of s square on both sides, then left hand side has no term containing s square. That means coefficient of s square on left hand side is 0. In right hand side, first we decide the coefficient of s square in this term, and it is clear that in this term coefficient of s square will be capital A. And here also, if we multiply this bs with s minus 1, we will have b into s square, that is coefficient of s square in this term is b. And if we multiply c with s minus 1, there will be no term containing s square. So by comparing the coefficients of s square, we obtain 0 equal to a plus b. Therefore b equal to minus a, and because a is 1, b will be equal to minus 1. So in the next step we write that comparing coefficients of s square on both sides of equation 1. As I explained, we obtain this equation 0 equal to a plus b, therefore b equal to minus a, and therefore b equal to minus 1. Therefore value of b we have obtained is minus 1. Now we decide how to obtain constant c. So if you observe, c is multiplied with s and constant term. So we can either compare coefficients of s on both sides, or we can compare the constant terms. In any case, we must obtain the same answer. So now suppose we compare the coefficients of s on both sides, then on left hand side coefficient of s is 5. In this term coefficient of s will be 2 times a. So here we will have 2a. Here coefficient of s is, if we consider this bs with s minus 1, we have bs square minus bs, that is minus b is the coefficient of s. Similarly, if we multiply s minus 1 by c, we will have cs minus c, that is plus c. So coefficient of s from last term is minus b plus c. We can understand in this way, bs multiplied with s minus 1 will give us bs square minus bs, that is coefficient of s is minus b. Similarly, c into s minus 1, cs minus c, so coefficient of s is c. So now we can write this. In the next step we write that comparing coefficients of s on both sides of equation 1, we have equation which we have obtained is 5 equal to 2a minus b plus c. 5 equal to 2a minus b plus c. Let me check again. 5 equal to 2a minus b plus c. A is 1, b is minus 1. Therefore 5 equal to a equal to 1, so we have 2a equal to 2, b is minus 1, therefore minus b is 1. plus c. So this is 3 plus c, therefore c equal to 5 minus 3, which is 2. So we have obtained these constants a, b and c. Now we substitute them, and we are able to write our function in terms of partial fractions. Our function is 5s plus 3 divided by, now our function 5s plus 3 divided by s minus 1 s square plus 2s plus 5 equal to, value of a is 1, so this is 1 divided by s minus 1. Value of b is minus 1. First we write this s square plus 2s plus 5. Here we have bs plus c. Value of b is minus 1 and value of c is 2. So bs plus c, that is 2. Let me check again. We are putting here b equal to minus 1, c equal to 2, that is minus 1 into s plus 2, and value of a is 1, so that we have substituted in this. Now we have to write or rearrange the terms in such a way that we have standard formula for inverse Laplace transform. For this term there is no problem, we have ready-made formula for the inverse of 1 over s minus something. Now for this, first I can take negative sign outside, and if you observe this, I can write as s minus 2 s square plus 2s plus 5. If I multiply by minus 1, I will have minus 1 into s plus 2. So I am writing this is 2 minus s, that I am writing as negative of s minus 2. Now this factor s square plus 2s plus 5 is irreducible. So what we can do is, we can find out the last term so that we have square of some linear factor, or we have perfect square. So if you observe, if I have first term equal to s square, second term equal to 2s, and if I consider last term as 1, then this is going to be square of s plus 1. If you square s plus 1, you will have s square plus 2s plus 1. So I can break 5 as addition of 1 and 4. I can rewrite 5 as 1 plus 4, and here I keep this as it is. Or you can decide the last term corresponding to these two. This is middle term, this is first term. We know that last term is obtained by square of middle term divided by 4 into first term. If we consider 2s as middle term, we have square of middle term as 4s square, 4 and into first term, that is s square. So if we consider last term as 1, we will have square here, perfect square. So now I keep this as it is, and this I can rewrite as s plus 1 square, and 4 I can rewrite as 2 square. Now you can think that we can write down this function again in this form. If you observe, we have seen this type of formulas for inverse Laplace transform. Suppose I have this type of formula, suppose I have this type of function s minus a over square of s minus a plus b square, then we have this formula. Because of s minus a, we write e raised to at, and if you observe, this look like s over s square plus b square. So function corresponding to this is cosine function, and because we have b square here, we write cos bt. So we will try to write this function in this form. For that, if I have square of s plus 1 here, I must write s plus 1, or I should adjust s plus 1 here if I want to write my function in this form. So that we can rewrite s minus 2 as s plus 1 minus 3. And if you recall, if I have instead of s minus a, if I have this 1 here, then this is going to be e raised to at sin bt divided by b. Okay, fine. So you must be clear about all these formulas which we have discussed in earlier lectures. So now we again rewrite this second term. This is as it is. Now if you observe this, I can rewrite as s plus 1 square of s plus 1 plus 2 square minus 3 times 1 divided by square of s plus 1 plus square of 2. And we can write one more step, 1 over s minus 1. If we take negative sign inside, we have s plus 1 square plus 2 square, negative negative positive, 3 divided by square of s plus 1 plus 2 square, and our function on the left hand side was 5s plus 3 divided by s minus 1 s square plus 2s plus 5. Let me check. 5s plus 3 s minus 1 s square plus 2s plus 5. Now we have ready-made formulas for all of this. So now we can apply inverse Laplace transform on both sides. Therefore L inverse of 5s plus 3 divided by s minus 1 s square plus 2s plus 5, this is equal to L inverse of 1 over s minus 1, which is e raised to t, minus, here we have s plus 1, that we can rewrite as s minus minus 1. So if we compare with s minus a, we have a equal to minus 1. Therefore we will write e raised to at, a is minus 1. Therefore we write e raised to minus t. And this is s over s square plus 2 square, something like that. So for that we write cos 2t plus 3 times L inverse of this. So here we have constant 1. So this will be corresponding to sine function. And we have s plus 1. So for s plus 1 we write e raised to minus t. And for 1 over s square plus a square we write sin at divided by a, that is 2. So this is required Laplace transform. We can rewrite this as e raised to t minus e raised to minus t cosine of 2t plus 3 by 2 e raised to minus t sin 2t. So in this way we can obtain inverse Laplace transform of this type of proper rational function. Here new thing is we have irreducible quadratic factor, therefore we are having this type of situation here. And we have written our function, first we have written our function as a sum of two partial fractions. Now first partial fraction is ready-made formula for inverse Laplace transform, but second one is not in standard, second one is not in such a way that we have ready-made formula for inverse Laplace transform, and this is irreducible. So first we write down, we adjust the last term so that we obtain perfect square. So we write 5 as 1 plus 4. Then we obtain here square of s plus 1. So for that we adjust s plus 1 in this way. We replace minus 2 by 1 minus 3. And we are able to write our function in such a way that we can use this standard inverse Laplace transform formulas. So to do this type of problems, you must be familiar with all these formulas. We have used these three formulas here. L inverse of 1 over s minus a is e raised to at. L inverse of s minus a divided by s minus a square plus b square, this is equal to e raised to at cos bt. And L inverse of 1 divided by square of s minus a plus b square equal to e raised to at sin bt divided by b. So you must be familiar with all these formulas, then only you will get the idea that I should write my function in this way. And remember, whenever we have irreducible factor, here we have s square plus 2s plus 5. Whenever we have irreducible factor in the denominator, we most probably have to write our function in this form, and most probably we will be using these two formulas whenever our factor is irreducible quadratic factor. Okay, fine. So I have tried to explain this method of partial fractions to obtain the inverse Laplace transform of this type of functions. I hope you like this lecture. Thank you very much.